Welcome back to the deep dive. Today we're tackling something pretty central in AI development. How do we actually make language models smarter after their big initial training phase? We know folks have tried things like reinforcement learning, RL, and seen some good results, but honestly, scaling that up, it often brings a whole host of problems. Think latency, memory demands, keeping the systems reliable. It gets complicated and expensive fast. So what if there's another way? Today we're doing a deep dive into a really interesting approach called Swarm Sampling Policy Optimization, or SAPO for short.
SAPO is quite different. It's designed as a fully decentralized RL algorithm for this post-training stage, asynchronous too. The main goal here is to let these LMs learn together, essentially sharing what they figure out across a network. Imagine a bunch of different computers, maybe running different setups, all contributing their experiences. It's meant to be a shortcut, really, to boost complex reasoning without hitting those typical scaling walls.
That sounds promising, because we have seen RL make a difference in reasoning. You look at models like DeepSeek R10, the potential is clearly there. But yeah, the practical side of scaling it up, that's always been the tough part. The delays, the massive memory needs, and let's be honest, the sheer cost of running huge synchronized GPU clusters reliably. It's a major hurdle.
And a lot of the common ways people try to scale RL involve distributed systems, where you absolutely have to keep the policy weights synchronized across all the different models training together. Those policy weights, they're basically the model's brain dictating how it acts. Keeping them all in sync is not just resource intensive, it creates serious communication bottlenecks. Especially with more models or bigger ones, you need really carefully built infrastructure just to keep things stable and running smoothly. It often becomes the limiting factor.
Okay, so if synchronization and centralization are the problem areas, SAPO must be doing something fundamentally different. You said decentralized.
Yeah.
A swarm of nodes. That sounds like a whole new structure.
It really is. In the SAPO setup, each node, each computer in the network, it manages its own model, or maybe even several models. And the key part is how they share. They pass around decoded rollouts. A rollout is just the sequence of steps a model took on a task, right? And decoded means it's shared in a simple format, like plain text, not some complex internal state. What's great is that this whole system doesn't need to worry about how fast the network is, or if all the models are the same type, or even what hardware is being used. Nodes can even just work alone if they want. This simple sharing avoids those scaling bottlenecks. It means when one model has a breakthrough, an aha moment, that insight can spread quickly through the swarm, lifting everyone up.
That flexibility is really key, isn't it? It's not tied down to one type of model or one learning algorithm or specific hardware. That really opens things up for lots of different people or systems to contribute without all that synchronization overhead you mentioned. It's kind of like a multi-agent system where all that diversity in models and data helps everyone explore better and generalize more effectively. And you mentioned the researchers specifically focused this on SLMs, right? Small language models.
That's right, models under 10 billion parameters. The kind you might run on your own machine, like a laptop or on-edge devices, makes it quite accessible.
Okay, so that's the architecture. But how does the swarm actually, operate? What's a step-by-step process for learning?
So you've got this network, let's say N nodes. Each one has a set of problems or tasks it knows how to verify, meaning it has the ground truth answers. First step, each node generates a bunch of answers for its questions. These are the rollouts we talked about. Then, crucially, these bundles of task and rollout data can be shared with other nodes, or other nodes can choose to sample them, and because they're shared in that simple, decoded format, any node can take a rollout, re-encode it, and figure out its value as if its own model had generated it. Doesn't matter where it originally came from.
Ah, I see. So nodes aren't just passively getting data. They're actively building their own training data sets. They pull some of their own rollouts and some for what others have shared across the swarm. And they get to decide how they choose which external rollouts to use.
Exactly. They have full control over that sampling. For instance, in the experiments they ran, the nodes first tossed out any rollouts that didn't actually improve things, ones with zero advantage, basically no useful learning signal. Then, from the remaining good stuff shared by the swarm, they just sampled uniformly, picked randomly from the helpful examples. This lets them filter and focus. Then, using its own local reward model, the node calculates the rewards for these chosen rollouts and updates its policy. And it does that using standard algorithms, things like PPO or GRPO, which are common ways to tune these models based on reinforcement learning signals.
Right, makes sense. So to see if this actually worked, they ran controlled experiments. What did that setup look like?
They set up a swarm of 8 Quen 2.5 models. These are pretty small, 0.5 billion parameters each. They ran them using PyTorch inside Docker containers, so it was a controlled environment.
And the tasks. What were the models working on?
They used a data set called Reasoning GYM. It's neat because it can generate loads of different problems on demand, covering things like algebra, logic puzzles, graph problems, number-based conversions, arithmetic, even propositional logic. And importantly, each type of problem comes with a way to automatically check if the answer is right. So reliable scoring. The models in the tests were generalists too. They got questions from all these areas mixed together.
Okay, and how did they vary the sharing part in these tests?
They had a baseline with no sharing at all. Each model just used its own 8 rollouts. Then 3 SAPO setups, one where models used 6 of their own rollouts and sampled 2 from the swarm, another balanced at 4 local and 4 external, and one leaning heavily on sharing with 2 local and 6 external. Each agent tackled 8 tasks per round and generated 8 different attempts or completions for each task.
And the results? Did this sharing actually help?
Oh, definitely. The balanced 4, local 4 external setup. It achieved the highest total reward across all the agents in round, something like 1093. Compared to the baseline, which only got about 562, that's a huge jump, a 94% improvement. Even the other sharing setups, the 26 and 62 configurations, were significantly better than the baseline where no one shared. It really showed how that aha moment from one agent could spread and lift the whole group. And interestingly, they initially thought about adding a reward just for getting the answer format right, but it turned out they didn't need it. The knowledge of correct formatting just spread naturally through the shared rollouts.
Wow, a 94% improvement is pretty striking. But it wasn't all straightforward, was it? There was a catch with relying too much on sharing.
That's right. While sharing was clearly good, the setup that relied most heavily on external data, the 2 local 6 external ones, showed some issues. It hit high rewards sometimes, but its performance swung up and down quite a bit as training went on. It seemed less stable.
Why would that happen? More sharing sounds like it should be better.
It's down to some subtle network effects, it seems. If a really good agent pulls too many answers from the shared pool, it might end up learning from the mistakes or less optimal solutions of weaker agents, which can slow it down or even confuse it. Also, there's a balance needed for the shared pool itself. If agents are taking out lots of rollouts, but the group isn't contributing enough high-quality ones back in, the overall quality of shared experience goes down. This leads to what they called steep learning and forgetting behavior. The models learn quickly from good shared data, but then might forget or regress if the pool quality drops. That explains those oscillations. So finding that sweet spot for sharing, like the 44 balance, seems pretty important for stable progress.
Okay, so the control tests show a clear benefit with a caveat about balance. Did they try this out in a less controlled, more, well, chaotic environment?
They did. They ran an open source demo involving thousands of people from the Gensyn community. This was really diverse, different hardware, different model versions, people contributing from all over, a real-world test bed.
How did they track performance in such a varied setup?
They had a central judge system. It would randomly pick reasoning GYM questions and send them to nodes, then score the answers it got back. This allowed them to compare models that were participating in the swarm against similar models that were trained completely on their own in isolation, and the results. Swarm training did lead to measurable improvements, but the size of the benefit depended on the model itself.
Interesting. What kind of differences did they see?
For those Quen 2.5 models, the 0.5 billion parameter ones we saw in the controlled tests, joining the swarm consistently boosted their performance over time. After about 175 rounds, normalized rounds, to compare fairly, the swarm models were clearly doing better than the isolated ones.
But not for all models.
Right. For slightly stronger models, like Quen 3 with 0.6 billion parameters, they performed about the same whether they were in the swarm or training alone. This kind of suggests that SAPO might be most helpful for what you could call mid-capacity models. Models that are capable enough to learn from diverse inputs, but maybe haven't hit their performance ceiling yet. It's also worth remembering, in that big demo, the nodes were just sampling shared rollouts randomly, without filtering out the less useful ones like they did in the controlled tests. So the shared pool probably had a lot of noise, rollouts that didn't offer much learning value. The thinking is that with smarter sampling strategies, maybe even those stronger models could see more benefit from the swarm in the future.
Okay, so let's wrap this up. SAPO seems like a genuinely novel approach, a fully decentralized, asynchronous RL for post-training. It lets all these different nodes manage their own models, but share their experiences, their rollouts effectively.
That's the core idea. It turns sharing experience into a fundamental advantage. Learning can spread across this diverse swarm without needing strict controls on latency or demanding everyone use the same model or hardware. It offers a really practical, scalable way to enhance reasoning in LMs through this kind of collaborative training. And the experiments back this up that balanced for, local for, external approach nearly doubled performance compared to no sharing. But as we discussed, there's that important finding about balance leaning too heavily on others' experiences can make the learning process unstable. Finding that right mix is key.
It really paints a picture of a different way to think about AI training, moving towards more collective intelligence.
It certainly raises fascinating questions, doesn't it? What happens when these decentralized AI agents get really good at sharing insights, not just raw data? How could those aha moments propagating through a network change how we tackle complex problems with AI? It's something to think about.